In this second Electrical Fundamentals module, we'll be looking at series and parallel circuits. We'll examine how the voltage and current vary within the circuits, and we'll formulate some rules that apply to each. Understanding these factors will help in your diagnosis of electrical circuits. Let's start with a definition of a series circuit. This is where the current passes through each element in turn without branching off to another circuit. I've got here a series circuit with 4 globes. I'm going to start by measuring each of the globes' resistance and then the total circuit resistance. So globe 1 is 1.9 ohms. Globe 2 is 1.75. Globe 3 is 1.8. And globe 4 is 1.9. To find the total circuit resistance, we just add those together. And if I measure the total circuit resistance, and our measured resistance is about 6.8 ohms. So you can see it's pretty much the same. From here we can start to formulate some rules that apply to series circuits. The first rule is individual resistances in a series circuit add up to the total circuit resistance. We'll measure the voltage across each globe and the supply voltage. I'll turn my circuit on and measure globe 1. 3.02 volts. Globe 2, 2.92. Globe 3, 3.06. Globe 4 is 3 volts. And the supply voltage is 12.12. As you can see, the individual voltages add up to the supply voltage. The second rule for series circuits is the sum of the individual voltage drops in a series circuit equals the applied or supply voltage. Using Ohm's law, let's calculate the theoretical current in the circuit. Current equals voltage divided by resistance. So we have 12.12 divided by 6.62, which gives us 1.83 amps. So the theoretical current is 1.83 amps. I'm now going to measure the current through each globe and then the total circuit current. The current through globe 1 is 0.33 of an amp. Through globe 2 is 0.33 of an amp. Globe 3 is also 0.33 of an amp. The current at globe 4 is 0.33 of an amp. I'll now measure the total circuit current. And again, I've got 0.33 of an amp. The third rule for series circuits. The current flowing in the circuit is the same at any point. Why was the actual current much lower than the theoretical current? To find out, let's calculate the operating resistance. We'll use Ohm's law again to work out the resistance using the supply voltage and our measured current. Resistance equals voltage divided by current. So resistance equals 12.12 divided by 0.33. Our resistance is 36.72 ohms. So the operating circuit resistance is 36.72 ohms. This is much higher than our first total resistance reading. The reason for this is the globes are hot. This affects resistance. The hotter the globes, the higher the resistance. What would happen if I changed one of the globes? I'll take out one of my 10 watt globes and put in a 21 watt globe. And I'll turn the circuit on. Straight away it looks as though the 21 watt globe doesn't work. But the same thing will happen no matter where I put it in the circuit. It's a series circuit. Does it follow the same rules? Let's check. I'll turn the circuit off. My meter's set up on resistance, and I'll start by doing the resistance of each globe. I've got 0.84, 1.7, 1.62 and 1.63. And if I measure the total circuit resistance, you'll see that they all add up to the same. So yes, it does follow that rule. What about voltage? I'll turn my circuit on, put my meter on voltage, and I'll now measure my voltage drops. .3 of a volt, 3.8 volts, 3.8 volts, and again a little over 3.8 volts. My supply voltage is 12.03. So we can see the sum of all the voltage drops equals the supply voltage. Now I check for current. Turn my board off. Set my meter up to measure current. Circuit back on. We'll now find 0.37. I'll try it over here. 0.37. I'll try the total again. 0.37. So even though it's behaving slightly differently, it still obeys all the series circuit rules. There's another rule that applies to series circuits. If I create a break in the circuit stops working. Doesn't matter where I create that break, the same thing will happen. From the test we did on the circuit, we saw that the lower the resistance, the lower the voltage drop. This is a very important relationship. Looking at this circuit, we'll calculate the voltage drop across each resistor. To do this, first we have to calculate the current. R1 plus R2 plus R3 equals 6 ohms. Current equals voltage divided by resistance. 12 divided by 6 equals 2 amps. Now for the voltage drops. Voltage equals current times resistance. The voltage drop at R1 is 2 times 3, which is 6 volts. At R2, it's 1 times 2, which is 2 volts. And at R3, it's 2 times 2, which equals 4 volts. The smallest resistance has the lowest voltage drop, and the largest resistance has the highest. Let's have another look at the rules for series circuits. Individual resistances in a series circuit add up to the total circuit resistance. The sum of the individual voltage drops in a series circuit equals the applied or source voltage. In a series circuit, the current flowing in the circuit is the same at any point. A break in the circuit will cause it to stop working as there will be no current flow. A parallel circuit is where the current is divided into 2 or more paths and then returns via a common path. I have here a parallel circuit. We're going to do the same measurements that we did for the series circuit. Resistance first. I'm using the same globes that I used before, so their resistance will be the same. So I'll just move on to measure the total circuit resistance. And you can see there it's just over 1 ohm. We can't calculate the total circuit resistance in a parallel circuit by adding the individual resistances together. In actual fact, if we add more branches to this circuit, the resistance will continue to go down. Rules for parallel circuits. The first rule is the total circuit resistance will always be lower than the lowest resistance in the circuit. There are formulas to calculate resistances in parallel. The first one is RT equals R1 times R2 over R1 plus R2. This is for two different resistors in parallel. As an example, 6 ohms and 8 ohms in parallel would be 6 times 8 over 6 plus 8. That would equal 48 over 14, that's 3.43 ohms. As you can see, that resistance is lower than either of the others. The next formula is for all resistors of the same value. We start with the resistance value and divide it by the number of resistors. If we had 3 6 ohm resistors in parallel, that would be 6 divided by 3, which equals 2. Again, you can see the total circuit resistance is less than the smallest resistance. The last formula is for any number of resistors of any value connected in parallel. The formula is 1 divided by 1 over R1 plus 1 over R2 plus 1 over R3. We'll use 2 ohms, 4 ohms and 1000 ohms. So that gives us 1 divided by 0.5 plus 0.25 plus 0.001, which gives us 1 over 0.751, which gives us a resistance of 1.33 ohms. Again, smaller than the smallest resistance in the circuit. I'll do the voltage drops on my parallel circuit. I'll turn it on and I'll go across each globe. 11.34, 11.33, 11.34, 11.35. And my supply voltage is 11.61. So you can see that each of the loads has the same voltage drop as the supply voltage, or pretty close to it anyway. The next rule for parallel circuits is the individual voltage drops in a parallel circuit equals the applied or source voltage. Let's have a look at the current flow in a parallel circuit. In globe 1, we've got about 0.63 of an amp. In globe 2, about 0.63 of an amp. Globe 3, close enough to 0.63 of an amp. And just on 0.63 of an amp on globe 4. The total current flow is now 2.5 amps. The third rule is, in a parallel circuit, the total current flowing in the circuit is the sum of the individual branches. If I remove a globe from a parallel circuit, it only affects that part of the circuit. It doesn't affect any of the other globes. If I create a break in a parallel circuit, it only affects that branch. It doesn't affect any of the others. That's one of the advantages of a parallel circuit. So the rules for a parallel circuit. The total circuit resistance will always be lower than the lowest resistance in the circuit. The individual voltage drops in a parallel circuit equals the applied or source voltage. In a parallel circuit, the total current flowing in the circuit is the sum of the individual branches. And a break in a branch of a parallel circuit will cause that branch only to stop working. Series and parallel circuits behave quite differently, even if using the same loads. The rules that were demonstrated apply to all series and parallel circuits. If you're unsure of anything in this module, review it again. A good understanding will ensure that you can confidently deal with electrical circuits. And always remember, training is the key to your success. Bye for now.